Dear classmates, welcome back to the introduction chapter. In this video, we are going to introduce the concept of test quality, which is measured by DPM, defect per million. We will also introduce two models to predict DPM and the two models to predict the yield. At the beginning of this chapter, we have shown this figure where test escapes represent the bad IC passing the test. This is what we don't want in our testing. So the concept of defect level represents the fraction of bad chip passing the test. Defect level can be measured by DPM, defective parts per million. Typically, if the DPM is less than 200, it's considered acceptable quality. If the DPM is larger than 1000, it's considered very poor quality. So, in summary, low DPM means good test quality. If you think 1000 DPM, which is 0.1%, is good enough, then consider this case. Suppose we have a system which has 20 IC. Each of the IC is 1000 DPM. So what would the system DPM be? For a system to work correctly, we require no defective IC in the system. So the system DPM is equal to 1 minus parenthesis 1 minus 1000 DPM, which is 0.1% to the power of 20, because we have 20 identical IC in this case. This results in 2% system DPM. That means if you sell 1 million systems to your customer, you will have to fix 20,000 of them. This is a very bad quality. So low IC DPM is very important for reliable system. Now it's time for a small quiz. Continue from our last slide. Suppose we have the same system which has 20 identical IC. Suppose now we improve our IC quality to 200 DPM. What would the system DPM be? Please calculate this question. Now, are you ready for the answer? The system DPM is equal to 1 minus 200 DPM, which is 0.02% to the power of 20. This will be 0.4%, which is much better than our previous case, which is 2%. We observed that in our last slide, the IC DPM was 1000. We reduced it by 5 times. And in our previous case, our system DPM was 2%. By improving the IC quality, we also improved the system DPM by 5 times. So, how can we measure DPM? If we want to measure DPM by real data, it would be very difficult. And even if we can do it, it's already too late. So can we predict it before the IC is tested and sold to the customer? We will introduce two famous models to predict the DPM. The first one is Brown and Williams model proposed by IBM, in 1981. It used the binomial distribution assumption. The second model is a gross model proposed by Bell Lab in 1982. It uses Poisson distribution. According to the Brown and Williams model, we can predict the defect level by this equation. Defect level is equal to 1 minus yield to the power of 1 minus fault coverage. In this model, yield means the fraction of total manufactured IC that are good. A high yield means very good manufacturing quality. This is an unknown parameter. It can be estimated by fab data or prediction model. We will get back to this point later in this video. Another parameter, fault coverage, means the fraction of detected fault. From this equation, fault coverage is equal to the number of detected fault over the number of total fault. High fault coverage means very good test quality. This is a known parameter which can be calculated by the fault simulator. Please see the fault simulation chapter for more details. This figure shows the relationship between defect level and the fault coverage. As we can see from this figure, if we improve the yield from 50% to 99%, the defect level will also improve. If we zoom in this area of 200 dpm, we can obtain this table. If the yield is 99%, the fault coverage required is 98%. If the yield is 50%, the fault coverage required is 99.97%. From this table, we can see that on the left hand side, it corresponds to a poor yield but very good test quality. On our right hand side, we can see that it corresponds to a good yield but poor test quality. So if we want to guarantee the defect level, we would require either a very good test or a very good yield. In this slide, we show a simplified proof of the Brown and Williams model. Let's assume that each fault occurrence probability is Q. Suppose this probability distribution is uniform and independent. Suppose there are totally T faults in the IC. We can detect D out of T faults by this test. By definition, fault coverage is equal to D over T. Let event A represent the event that an IC is good. So the probability of A is the probability that an IC is free of any defect. So probability A is equal to 1 minus Q to the power of T. At the same time, yield is also equal to probability of A. Let event B represent the event where an IC passed the test. So the probability of B means that an IC is free of D faults. So probability of B is equal to 1 minus Q to the power of D. So event A, B means that an IC is good and it passed the test. Assume that there is no overkill in our test, so probability AB is equal to probability of A. By looking at all the above equations, we can now calculate the quality level QL, which represents the fraction of good IC passing the test. QL is the conditional probability of A given B. We can write this as probability AB over probability of B, which is 1 minus Q to the power of T minus D. We can extract T so that we have 1 minus Q to the power of T, which is our yield, and 1 minus D over T, which is 1 minus fault coverage. So defect level can be calculated as 1 minus quality level, which is 1 minus Y to the power of 1 minus FC. We can verify this by the Motorola experiment. In this experiment, we produced 18,500 chips, and we applied test number 1, of which the fault coverage is 96.6%, followed by a nearly perfect test, of which the fault coverage is 99.9%. In the second test, 103 IC failed. So this would be the test escape if we only apply test number 1. In this experiment, the number yield is equal to 12,056 over the total number of chips, which is 18,500. The fault coverage of the first test is 96.6%. If we use the Brown and Williams model to predict the defect level, that will be 14,454 dPm. However, according to our experiment, the defect level is 8,471 dPm. That means 103 IC over the total of 12,159 IC passing test number 1. These two numbers are pretty close enough, but they are not perfect. We will discuss the reason later. Now, it's time for a small quiz. Use the Brown and Williams model. Suppose that the yield is 98% and the fault coverage is 70%. Please predict the defect level. Question number 2. Suppose that your boss is not very happy about the defect level you calculate in the question number 1. If we add some design for testability DFT circuit to this IC so that we can improve the fault coverage, but the penalty is that the yield is reduced by a little bit. Suppose that the yield now dropped to 97% and the fault coverage has significantly improved to 99%. Please calculate the defect level again. Now, are you ready for the answer? If we plug in the number, which is 1 minus 0.8 to the power of 1 minus 0.7, this number would be approximately 6042 dpm. This is a very large number. If we plug in the same number to the second problem, that will be approximately 304 dpm, which is much better than question number 1. From this quiz, we can know that DFT is very important to improve the defect level, although it has a slightly penalty in the yield. Now we will move on to the second model, the Aguros model based on the Poisson distribution. There are two reasons why Brown and Williams model is not accurate enough. The first reason is because fault coverage does not represent defect coverage. That means even we have 100% fault coverage, it does not necessarily lead to 0 dpm. Even if we know that we can detect D faults out of a total of T faults, we still don't know how many defects can we detect among a total of how many defects. The detail of this point will be discussed again in the fault modeling chapter. The second reason is that instead of uniform distribution, defects are actually clustered. So in Aguros model, they propose to use the Poisson distribution. If we use the Aguros model, we will come up with the conclusion the defect level is equal to this equation. The detailed proof of this equation can be found in the appendix. This model is based on the observation that actual data showed defects are clustered. In this model, fault coverage is FC, Y is yield. We already know that from our previous model. In a Aguros model, we have a new parameter N, which represents the average number of defects on a bad die. As is shown in this figure, there are 3 bad dies and 7 defects. So the N is equal to 7/3, which approximately equals to 2.3. In a Aguros model, we need 2 parameters. One is N, which can be obtained from experiment, and the other is yield, which can be obtained from fab or estimated by prediction. Let's revisit our Motorola experiment. According to the experiment, defect level is 8,471. The Brown and Williams model shows that the defect level is 14,454. If we plug in the number using n equal to 1, the defect level would be 17,849 dpm. If we plug in the number 2 for n, the defect level would drop to 6,869. So according to the experimental data, the actual value of n is somewhere between 1 and 2. So now we still have one more parameter to predict, which is the yield. So how can we measure the yield? If we want to measure yield by real data, it's already too late. Can we predict it before mass production? In the following video, we will introduce two models for yield prediction, a simple model and a model based on critical area. We can use a simple model to estimate the yield. Assume that the number of defects K is Poisson distribution with mean lambda. So probability of K is equal to the probability of exactly K defects on a die. So a die is good when K is equal to 0. This figure shows the Poisson distribution with lambda equal to 2. Probability of K can be written in this equation. If we plug in K equal to 0, then we can obtain that the yield is equal to e to the power of minus lambda. Let's assume that the total die area is A and the defect density is D. Then lambda will be equal to AD, which means the average number of defects per IC. So we can know that Y is equal to exponential to the power of minus AD. That means if we have a larger die area, the yield will be lower. Now it's time for a small quiz. Based on the simple yield model, assume that the die area is 0.8 centimeter square and the defect density is 0.5 per centimeter square. So what is the yield based on these two numbers? Have you found the answer? The answer would be Y equal to exponential to the minus 0.8 times 0.5, which is approximately 60%. Based on this reasonable die size and the reasonable defect density, the yield seems to be pretty low for IC product to be profitable. The problem with the simple model is that some areas are actually not sensitive to the defect. So if we use the total die area A, it's a pessimistic estimation. So we would propose to use the concept of critical area, CA. CA of R means the area where the center of the defect of radius R length to create a fault. For example, suppose we have two metal wires and the circle represents a defect. The rectangle in the middle represents the critical area for bridging fault. If the center of the defect lands inside the rectangle box, then we would create a bridging fault. If the center of the defect is outside of the rectangle box, then we do not have a bridging fault. Similarly, figure B shows the case for an open fault. Consider one single metal wire, shown in the blue rectangle. The dashed rectangle here in the middle represents the critical area for the open fault. if a defect center is landed inside of the critical area, we can create an open fault. However, if the defect center is outside of the box, then there is no open fault. Before we can actually calculate the yield, we would need another function called the defect size and the density distribution, DSDD. The DSDD function can be written as D of R, which is the defect density per unit defect radius R. D of R can be modeled as a combination of two functions. When the defect radius is smaller than the threshold x0, we would expect a linear growth. When the defect size is larger than the threshold x0, we expect an exponentially decay function. So we can model D of R as two pieces of functions. When the radius is smaller than the threshold, we would have a linear function. If the radius is larger than the threshold, we have an exponentially decay function. The exact DSDD function is process dependent, but we show some example values here. The threshold x0 can be between 4.5 to 5.5 times 10 to the power of -6 centimeter. The exponent can be between 2 to 3. And the total defect density can be 0.25 to 0.6 per centimeter square. The total defect density, D0, is equal to the integration from R equal to 0 to R equal to infinity of D of R. That means the area under this curve is the total defect density, D0. So now we can estimate the yield based on the critical area. Again, we assume the number of defects follows the Poisson distribution with mean lambda, where lambda is the expected number of defects per die landing in the critical area. So we take the integration from R equal to 0 to R equal to infinity, Ca of R times D of R, dr. Now the yield can be written as exponential minus lambda, where lambda can be the integration function. Compared with the previous simple model, our new model is more sophisticated. Critical area analysis is a very useful tool to estimate the yield. It has two important functions. If we use critical area analysis function, we can improve the design to improve the yield. For example, given this layout, after critical area analysis, we see some hotspots where the critical area are highlighted in red color. We can somehow change the layout a little bit to remove the critical area in the middle, so that we can improve the yield. The number 2 function of the critical area analysis is to extract bridging or open fault for test generation. For example, as we can see, the critical area down here cannot be improved, so we can extract the fault list for test generation. In summary, in this video, we have introduced the concept of test quality, which can be measured by DPM. There are 2 models for DPM. One is Brown and Williams model, which is very simple but not accurate. And the second model is a gross model, which requires an additional parameter, N. We also introduced 2 models for yield. The simple model, which is exponential minus AD. The critical area model can be obtained using the critical area. Now it's time for thoughts. In our critical area model, we introduced the DSDD function. So what is the unit of the function d of r? Remember, d of r is equal to the defect density per unit defect radius r. So please tell me the unit of d of r. Thank you for watching.